Welcome again to the podcast of the Flinn equation worksheets. I last time did A through K, and we're going to see how far I get. I'm going to start on a letter L. So if you're following along, that's M. Just following along, first one on L, we have solid ammonium carbonate. So again, if you see the word solid, then you have to leave it together, write it all out. So ammonium has a 1 positive charge. Carbonate has a 2 negative charge, so that will be NH4 2CO3, and it's just heated. So arrow, little triangle that indicates it's heated. It's not necessary actually to put a triangle from the AP perspective, not a bad idea. Now here we have a salt that contains oxygen. This is kind of the opposite of a metal oxide and a non-metal oxide, so you're going to make a metal oxide and a non-metal oxide, although ammonium is not a metal, but you can make NH4 2O plus carbon dioxide. Now, this is a little bit of a strange thing. I'm not sure I totally agree with the key that I have sort of in front of me. They say that this turns into ammonia and water, and that's kind of there. And so I could go with that. So, anyways, what type of reaction is this? This, of course, is a decomposition reaction. I think you're going to need, no, it's already balanced. All right, let's look at this next one. This next one's kind of a classic one, a solution of hydrogen peroxide. Now, hydrogen peroxide is H2O2. You don't dissociate that. Peroxide likes to stick together with water, is catalytically decomposed. There's some kind of a catalyst here. You don't necessarily need to write the little catalyst there, but it's a redox reaction. Basically, the O in here is peroxide, which is O2 -2, but the oxidation number is -1, which is very uncommon. As you probably know, oxygen would rather be either oxygen gas, 0, which is one of the products, or would like to be O -2. But O -2 never exists by itself, so the other substance that it makes, of course, would be water. Now, to balance this reaction, you'll need to basically put a 2 here and a 2 here. Name the element being reduced and the element being oxidized. Tricky question. The element being reduced is oxygen, and the element being oxidized is oxygen, because the O is going from -1 to O2 with a 0 charge, and the O is going from -1, and it's going to O -2. This is in the water. So here it's going down in -1, 0. This is going up in charge, so this is being oxidized and this is being reduced. So it's kind of a weird deal that it's the same substance is both oxidized and reduced. All right, let's look at letter N. A solution of potassium iodide. So if you have a solution of potassium iodide, you would write K positive plus I negative. You dissociate it because all potassium things are soluble. It's electrolyzed. At which electrolyte? Now, the other thing, when it says a solution, what does that imply? It implies that you've also got water present. So we need to add water here, and it's electrolyzed. So as it's electrolyzed, the I minus can jump up to I2. But we do have an issue, don't we? We need to figure out what's going to happen. Who is going to, that's going from -1 to 0 from an oxidation number, -1 to 0. That's going up. I need to find something to go down. All right. Now, potassium has a +1 charge. Could he drop to regular potassium? Not likely. Potassium is a highly, highly reactive metal. Hydrogen is +1, and O is -2. O at -2 cannot go down. There's no such thing as O -3, so that means the other product must be hydrogen gas. So now we have a classic redox reaction that needs actually kind of like a more involved balancing. So I minus goes to I2. You have to put a 2 here, plus 2 electrons. And then you've got water turning into hydrogen. Now we need to say, all right, and it's it would be it didn't say if it's a basic solution or an acidic solution. So as water turns into hydrogen gas, well, you've got O's and like OH's. You might really think of this as like HOH. And so if you add hydroxide to this side, that's going to have to be it. So to balance this, you're going to need a 2 here, if I'm not mistaken. 2, and then a 2 here. Yeah, that's correct. And that means we have 2 electrons here. And then the electrons, as you can see, will cancel. This is a pretty involved question in my mind. Balancing it is you have 2I negative plus 2 waters makes I2 plus hydrogen plus 2 hydroxides. Kind of an involved balancing. At which electrode would a gas be released? Now remember, oxidation occurs at the anode and reduction occurs at the cathode. So you're going to produce the hydrogen gas, and the hydrogen is going from +1 to 0, so it's a reduction. So reduction occurs at the cathode. So at the cathode, you will make hydrogen gas. That's kind of a, hopefully they don't give us one quite that hard. Letter O, a solution of copper 2 sulfate. All right, if I see a solution of copper 2 sulfate, I'm going to dissociate it. All right, Cu2 positive plus SO4 2 minus. Is electrolyzed using inert electrodes. Is it acidic, basic, or neutral? Again, what's the other thing you always got present going? Well, you got that water. So this is going to be kind of similar to that last one. So the copper, if you've got the solution, copper can turn, copper ion, copper 2 positive, can turn to copper. And so that's the reduction. So we need something to oxidize. That means it needs to go up in charge. Hydrogen's at +1. O is at -2. Now in this case, it's kind of the reverse. The O in water can go up. Sulfate is as oxidized as it can get. Sulfur cannot be more oxidized than that. So you're going to have Cu2 positive turning into Cu. Since this is redox, I'm going to try and do them in the half reaction method. And the water is going to turn into oxygen. And then the other product is simply hydrogen. And to balance that out, I would need a 2 here, and I believe a 4 there. That's correct. And that would require 4 electrons, and this would require 2 electrons. So when you balance the equation, you're going to have to double, because you want the electrons to cancel the coppers. So that'll give us 2 Cu2 positive plus that would be 2 waters, and that's going to make 2 coppers plus oxygen plus 4 hydrogen. Is the solution acidic, basic, or neutral? Of course it will be acidic of the hydrogen over here. Okay? Letter P. A solution of ammonium sulfate. All right, it's a solution, so I'm going to write NH4 positive plus SO4 2 minus is added to a saturated solution of barium hydroxide. All right, so then we're going to leave the barium hydroxide together. And as you add this, one thing you'll notice, you've got sulfate and you've got barium. This is a classic precipitation reaction, and barium and sulfate is, of course, a insoluble sulfate. Remember, all sulfates are soluble with a few exceptions: barium, calcium, lead, and barium's one of them, of course. And so that leaves us with ammonium hydroxide. So ammonium hydroxide, now what do you do with that one? That's kind of a weird one. Ammonium hydroxide essentially is, so you can write it as NH4OH, just basically kind of a classic double replacement. But ammonium hydroxide usually expresses itself as ammonia plus water. It's kind of the opposite of that sort of acid-base thing. So that is a better answer. Now to balance this reaction, we were going to need, I believe, a 2 here. Yes. Now, by the way, it would also be appropriate to write Ba2 positive plus 2OH minus. It's kind of debatable because, you know, I've seen barium hydroxide, and I know that barium hydroxide is a precipitate. I actually, you know, since they said saturated, I would go with this one right here. Yeah. All right. Identify any precipitate form. Well, I just kind of mentioned that the precipitate is barium sulfate, so that was in our earlier discussion. That was a pretty easy second part. All right. Letter Q here. A solution of copper 2 chloride. Again, if it's a solution, we're going to dissociate it. All right, and a solution of sodium, Na positive, sulfide plus S2 minus. Now you got to just know your solubility rules. The key on this is know your solubility rules. A sodium chloride, of course, if you put those together, they would be soluble, so that's not going to make a precipitate. This is a classic precipitation reaction. Sulfides are not generally soluble. That's the answer. Name the spectator ions. Oh, who are the spectator ions? The spectator ions are sodium and chloride. All right, what's our next one? Letter R, solution of manganese sulfate. Now, since it says it's solution, the Mn2 positive and the sulfate are apart. And that's not one of the sulfates that's insoluble. Plus ammonium. Ammonium, of course, is NH4. All ammonium things are soluble. Plus sulfide. Sulfide is a classic thing that makes precipitates. So that's just going to make MnS. Ammonium sulfate. They're both spectators and they fall out. Listing a precipitate that forms, that right there, of course, is the precipitate. That was a precipitation reaction. We hope we get one like that. Letter S, so a solution of silver nitrate, so silver, positive, plus a nitrate, negative. Again, all nitrates are, but if they say solution, you should dissociate it, is mixed with sodium chromate. And it's a solution too, so sodium would be Na positive, and chromate, kind of a weird one, CrO4, 2 negative. Sometimes it's hard to remember that. Chromate loves to make precipitates. So this is going to make the precipitate Ag2CrO4. Your sodium nitrate is a classic thing to drop out. You do need to balance it by putting the 2 here. What is the oxidation number of chromium in the chromate ion? Now to do that, of course, you've got CrO4, 2 negative. O always has a negative 2 charge, so that's negative 8 because there's 4 of them, and that equals negative 2, so it's X plus negative 8 equals negative 2. X would be 6, so it is Cr. It's plus 6 is the oxidation number on that. All right, next one says glacial acetic acid. That's just acetic acid. Glacial means it's pure acetic acid, so you can write it as HC2H3O2. By the way, you can also write this as CH3COOH. It's just, this is the more organic way, and this is the less organic way, is mixed with a solution of methanol. Now, methanol, if you have the anol ending, that makes it an alcohol, and methyl means there's 1 carbon, so it would be C. Sometimes I think it's almost better to draw it structurally. COH, H, H, H. Now, this is sort of a classic organic reaction. If you take an acid and you mix it with a organic acid and you mix it with an alcohol, you always make an ester. Actually, it might be better to use it in this fashion, because if you were to say this, acetic acid, I can't talk here, makes, this is its structural formula, and I'll put this here for H's. And so what happens is that you form water, kind of the OH here gets together with this H, and this O connects here. So if we were to draw this structurally, you would have C, C, double bond O, O, C, and then you would make these H's. And then it kicks out water. And it would be acceptable, certainly, to draw it structurally instead of this right here as the answer. I would think would almost be better. And what type of reaction is this? This is called an esterification reaction. I doubt on the AP test they're going to give it an organic question, to be honest with you. Letter U, chlorine gas. All right, that's Cl2. Remember, chlorine's one of those things that always gets a 2 diatomic into a cold dilute solution of potassium hydroxide. So that's plus K positive plus OH negative. This is actually one of the trickier ones I think they could ask you. See, the chlorine, I think it's obvious that the chlorine needs to change its charge, and most of you realize that chlorine likes to change to chloride. But then you've got to find something, so that's going from a 0 charge to a -1 charge. Now you need to find something that's going down, so that's reducing. You need to find something to go up. And the classic thing is you want to think it has to come from here, but it turns out that the chlorine in a dilute basic solution, you should have this memorized, we've talked about this, will go up to the hypochlorite ion. So the chlorine is going to be both reduced and oxidized. So this is kind of an ugly balancing thing, though. Cl2 goes to Cl-. We have to do the classic redox thing. So that's that reaction. And then we've got Cl2 also turning into ClO-. Now this is in a basic solution. They're just giving it, it's a basically, R is in a basic solution. So now we need to balance our waters with oxygen, or oxygens with water. I didn't say that right. And then you would add 2 hydrogens on this side. But of course it's basic, so then we add 2 hydroxides to both sides, plus 2 hydroxides. This, of course, makes 2 waters, but that cancels off 1 water, and this becomes just simply water. Now, when I balance the charges, I have a -2 charge on this side and a -2 charge on that side. What have I done wrong? What did I do wrong? I made a mistake. Oh, yeah, I got it. Okay, I'm going to redo this. The chlorine goes to 2ClO minus, and when you balance it with the water, I need to put 2 waters on this side, and that makes 4 hydrogens, and I need to then add 4 hydroxides. This becomes 4 hydroxides, and this becomes 2 waters, and I have 2 waters. So these 2 waters go away, go bye-bye, and you get 2 waters on this side. Now, in terms of charge, the charge on this side is -2, on this side is -4, so we're going to add 2 electrons to this side. That was a lot of work. All right, and the 2 electrons from here and here cancel, so we're going to have 4 hydroxides plus, now in terms of chlorines, we've got chlorines in both the oxidation reactions. There's 2 chlorines, and that's going to make 2 chlorides plus 2 hypochlorites plus 2 waters. There's a nasty one. Okay, what element is undergoing oxidation and what element is undergoing reduction? Of course, the answer to this is the chlorine is undergoing both oxidation and reduction. All right, letter V coming up here. I think I just clicked the button here. We're getting a signal that we're in wait mode. All right, here comes V. A strip of copper, Cu, hello, things slowing down here, is immersed in concentrated nitric acid. Since it's a nitric acid, you should know it's a strong acid. You dissociate the nitric acid. And it's concentrated. When you see concentrated, that's actually going to give us a name. The copper obviously has to change its charge. The most common charge of copper is 2 positive. You probably could write 1 positive. So that's going up. You're going to look for something to go down. Now, this is a classic example. This is the one time where nitrate actually can turn into something different. And what it can turn into, if you're not familiar, is to nitrogen dioxide. And to balance that, you'll need water. So, but to truly balance this, you should probably do the half reaction method. Cu goes to Cu, 2 positive, plus 2 electrons. That's easy. And then the nitrate goes to this. It's a brown gas, and in our class, we certainly did do this reaction towards the beginning of the year. Now, to balance this, you would want to add some waters to get some additional oxygens, and then you would need 2 hydrogens. I believe that balances it in terms of the elements. I got 1 N, I got 3 O's, I got 2, yep, that's it. So the charge on this side is plus, this side has a 0 charge, this side has a +1 charge, so I'm going to need 1 electron on this side. Now, to add these, I'm going to have to multiply this reaction by 2 so I can get my electrons to cancel. So that's going to be 4H positive plus 2 nitrates plus copper goes to copper, 2 positive, plus 2 NO2 plus 2 H2O. All right, list at least 2 observations that indicate a chemical reaction is occurring. It's going to give off a brown gas. You need to almost have seen this reaction. And the copper, which is a metal, is going to make the solution will be blue. I don't know what other else ones. It's going to be highly exothermic, and you're going to see a bubbling of a gas, a color change. I guess you'd say color change. That would also work. So, yeah. Letter W. All right, a little easier than the last one. All right, letter W, hydrogen gas. All right, we're waiting for it to appear here. We're having some pauses. Maybe I'll just pause the whole show and then repeat here in a minute because we've lost the... hello. My software is having issues here. I think what I will do is stop it and I will restart at letter W. Oh, maybe I can. All right, here's W. All right, sorry about that. We had some weird glitches there. Hydrogen gas, so that's H2, is passed over hot iron 2 oxide. That would be FeO2. Again, this is going to be redox. If you've ever got an element, it's going to be redox. Hydrogen has a 0 charge, Fe has a +2 charge, and O has a -2 charge. But if you've got an element by itself, he has to change his charge. So if hydrogen's at 0, his most common charge, of course, is +1. So he's going to go to H +1. I'm going to put that over there because this is not really, there's no water around, so he's not going to make like a hydrogen ion. And so that's going 0 to +1 up. You've got to find something to go down. Now, if you look at it, the thing that can go to O can't go less than -2, so the iron has to drop. So if the iron drops, he has to drop to iron. And that leaves H positive and then the O -2. That simply makes water. And then I don't think we need to balance this using half reactions. In fact, it's balanced. What is the oxidation number of the hydrogen in the hydrogen gas? By definition, if it's an element, it has an oxidation number of 0. Not terribly to X. Acidified potassium permanganate. All right, potassium would be K positive plus MnO4 negative. If you ever see permanganate, you've got to realize it's probably redox. I'm just looking at this. I'm kind of doing these cold turkey here. Is added to a solution of sodium Na positive, because it's a sodium, nitrite, NO2 minus. Watch that, nitrite. And it's acidified. So if you should memorize that permanganate will turn in an acidic solution, it will turn into Mn2 positive. So you got that's a reduction. You got to find something to go up. If you look at the sodium and the potassium, they will not go up. The nitrite can go to a higher oxidation number, which is the nitrate. Then we need to do the balance thing. This is a more complex balancing. MnO4 minus is going to turn into Mn2 positive. My manganese have balanced. So now I'm going to add 4 waters. And then I'm going to add 8 hydrogens. Now, when you do the math here, there's, I believe it's 5 electrons I need to add somewhere. 8 minus 1, 7. This is +7 side, and this side has a +2 charge, so I'm going to need 5 electrons on this side. Now, for the nitrite, NO2 minus, that goes to NO3 minus. I need to add some water on this side to get the O's, and that's going to make 2 hydrogens on this side. Charge on this side is -1. Charge on this side is +1. So I'm going to have to add 2 electrons to this side to cancel it out. Now, we have 5 electrons and we have 2 electrons, so I'm going to multiply this reaction, the top reaction, by 2, and the bottom reaction, I'm going to need to multiply by 5. Now, we do have an issue. We've got water in both reactions, so and hydrogens for that matter. So this is going to become 16. I'm doing the hydrogens first, and this will become 10. And so 16 and 10. Okay, but you'll see that in a second. Let's do the waters. This will be 5 waters here, and this will be 8 waters. And while we're at it, let's go ahead and be 2 here and 2 here, and this will be a 5, and this will be a 5. So the hydrogens, there's more hydrogens on the product side, and so I'm going to have to put 6 hydrogens here, and then the 2 permanganates. That's kind of a given, okay, and the 5 nitrites. And that's going to make 2 Mn2 positive plus 5 nitrates. And then we're going to have to put the waters. I got 8 on this side and 5 on this side, so that'll be plus 3 waters. Kind of a long balance, right? And balance the oxidation half reaction for mass and charge. Okay, well, guess what I just did? I did that. These are the half reactions. If they want to balance it, that's the way you would balance it. So by doing anything, that solves all that problem. So you don't have to ask an additional question. A solution of sodium, I say solution, is sodium bromide, so that'd be Na positive plus Br minus. I bet Br minus is going to change its charge. It's added to acidified solution of potassium bromate. So that'd be potassium. And bromate's like chlorate. Chlorate's ClO3 minus. Bromate is BrO3 minus. Okay, now, it's acidified. Now we've got the bromide, and it's acidified. If they say it's acidified, you know you've got a redox reaction. So the bromide can turn into bromine. All right, it's going from -1 to 0. Now the bromate is at a much higher charge. I'm not sure it's plus something. We could figure it out if we have to. But most likely, he's going to go down. He's going. The bromide went up, and so the bromine, or the Br and the bromate needs to go. This is one of those ones that are going to both turn to the same thing. I think this is called, I lost the term. There's a term for this. Br minus is going to go to Br2. Okay, and that's 2 plus 2 electrons. And then the BrO3 is going to turn it minus, is going to go to Br2. It might go to like a hypobromate or bromite. I don't know. I think I'd go with this one. Okay, I just got interrupted. Let's get back to the problem. BrO3. Put a 2 here to get the bromines balanced. It's acidified, so I'm going to have to add some water on this side. There are 6 oxygens, so I'll need 6 waters, and that's going to make 12 hydrogens. The charge on this side would be 12 minus 2, which is plus 10. The charge on this side is 0, so I'm going to require 10 electrons on this side. How ugly is that? So this is going to be multiplied by 5. So we're going to require, will be 12 hydrogens plus 2 BrO3 minus plus 10 Br minus, because this right here, of course, 5 times 2, this becomes 10, and this becomes a 5. And then that's into 6 Br2s plus 6 waters. And that is essentially the answer. Let's see if they agree with my assertion. They've got a different balanced reaction. What have I done wrong? Oh, you know, this reaction is, everything's doubled here, isn't it? You could probably put a 6 here, a 1, a 5, a 3, and a 3. It's the same thing. You're not going to get marked off if you do it that way. All right. I'm going to just do, this will be the last one. Aluminum metal. So that's Al is added to a solution of copper to chloride. All right, at least, okay. What's going to happen? Well, the aluminum has no charge, so he has to go up to an Al plus 3. The only charge you've ever heard of for aluminum is plus 3. And for copper, this is a simple redox. The copper is going to drop down the copper. The chloride is a spectator. Now, that's not a balanced equation. Now, the number of coppers and aluminums is balanced, but the charges are not balanced. Now, you could do this using the half-cell reaction. Well, let's do it that way. Cu2 positive goes to Cu. Add 2 electrons on this side to balance it. And the Al is going to go to Al3 positive plus 3 electrons. And if you can see this, you need to multiply this reaction by 3 and this one by 2 when you add them all up. So that's going to make this, of course, a 6. This will be a 3. This will be a 3. This will be a 2, and a 6. And, of course, the electrons cancel, and so that's what we're shooting for. So you're going to have 3 copper, 2 positive, plus 2 aluminums makes 2 aluminum 3 positives plus 3 coppers. All right, list at least 2 observations that indicate a chemical reaction is occurring. 2, yuck. Okay, first of all, copper 2 positive is blue, and copper metal is a coppery colored, how's that for a word? A coppery sort of goldish colored metal. So what's going to happen is the solution is going to go from blue to clear. You're also going to see the aluminum is going to disappear. You have a shiny silvery metal, and actually the copper is going to form on the aluminum. This is sort of a classic reaction. 2, I would say that you're going to go from blue, the solution is going to go from blue to clear, and you're going to see a precipitate form, which will be the formation of the copper, and you're also going to see the aluminum is going to disintegrate. That's 3. They asked for 2. All right, that's good. I'll do another podcast a little bit later, but these are some more reaction stuff that would be very useful for you. So have a great day.